Thank you very much for the kind introduction. My name is Andreas Weisheit. And I'm working for Linde as Head of Market Development Solar. I'm going to talk about high-performance, low-cost solar cells and the role of gases and liquid precursors. Very quick introduction of our company. Linde is a 13.8 billion euro enterprise. We are doing business in more than 100 countries globally. Our business is structured in two divisions. Gas division is a leading global supplier of industrial gases to different industries. Our engineering division is a specialist in engineering and constructing of cryogenic plants, petrochemical and other chemical plants. Our strategy is focused on three global megatrends which should be driving our growth. One is emerging markets, one is clean energy, and one is healthcare. Solar photovoltaic fits in very nicely between emerging markets and clean energy because it's an ultimately clean source of energy, and industry is growing in the emerging markets like China and Taiwan. In the current environment of the solar industry of overcapacity and consolidation, reduction of costs and improving of efficiencies is more important than ever. Materials address all the cost levers in this area. The industry is striving towards reducing the dollars per watt or euro per watt in order to achieve grid parity. There are two sides of the dollar per watt equation. One is the dollar per square meter, the other one is the watt per square meter. The cost levers to address this equation is material costs to reduce the dollar, throughput to increase the square meter, efficiency to increase the watt, and yield to improve the square meter. The role of gases and chemicals to address this is local production. Localizing production can reduce material costs, same way as recycling, gas and chemical recycling. Another area which I will talk to in one of the next slides is fluorine, which is used for PECVD chamber clean, which can simultaneously increase throughput and reduce material costs. There are a lot of new materials and processes, which I will cover with my presentation, which can both increase the throughput of the manufacturing lines and improve cell efficiencies. And last but not least, it's also important to look at the purities of chemicals and gases, which can both reduce material costs if you can go to lower purities, or can improve efficiencies or even the yield if you go to higher dedicated purities for the solar industry. Another way to look at this, another way to categorize this, is to separate supply chain solutions and application-driven solutions. In supply chain solutions, materials and gases can contribute directly to material cost reduction, which can be done by on-site production or by chemical and gas recycling. The other area is application-driven, where new materials are necessary and new materials enable new processes like selective emitter, like backside passivation, like N-type solar cells, advanced texturization, or high-efficiency CVD chamber cleaning. As the solar industry is growing capacity, economies of scale make more efficient, more cost-efficient supply chains, supply schemes of industrial gases available. Today, most of the gases that are used in the solar industries are coming out of big gas production centers where gases are liquefied and then shipped via trailers to the customer, or the trailer is going to a cylinder filling station where it's transfilled into smaller packages and then transported to the customer. When the industry is scaling, growing the scale to gigawatt and several gigawatt, on-site production becomes available, becomes economically viable, and this on-site production cuts out energy costs for liquefaction of gases or cuts out costs of refilling. And this is relevant for nitrogen, which is needed for cell and module manufacturing, for oxygen, which is used in cell manufacturing, and also for hydrogen, which is used in the polysilicon industry. Another area which is another possibility, another supply scheme which is has the lowest cost and is becoming very popular in Asia is the gas supply via pipeline in industry cluster segments, which is very common in Taiwan or in China. Along this chain, as economy of scale is moved from a cylinder to liquefied to on-site or pipeline supplies, the cost of the gases will be reduced. Beside on-site production, recycling is a very nice opportunity, not only to reduce the costs, but also to improve CO2 footprint of the supply chain and in order to enable supply chains. One example of this that I'd like to talk about is argon. Argon is used in very big quantities in the production of silicon ingots, which are then sliced into wafers. During the ingot melting, argon is needed for inerting, as the ingot melt at very high temperature has the risk of forming silicon oxide or silicon nitride in contact with air. That's why argon is used. On-site production of argon is economically not viable, since argon is a byproduct of oxygen production. In order to make argon in an efficient way, you need to make 5 parts of oxygen to make 1 part of argon. So on-site production without oxygen doesn't make sense. However, since argon is an inert gas, it's not consumed, it's not reacted in the process, but it is diluted with nitrogen, oxygen, CO2, moisture, CO, and methane, and other hydrocarbons in the exhaust stream. Recycling and purification technologies exist to recover most of the argon from the process. It's basically what gas companies are doing 24 hours a day and 365 days a year. We take out argon from the air, purify it, separate it from the other molecules, and purify it up to 6-9 purity. And this technology can be applied at a certain scale in the ingot industry to recover the argon from the process. This recycling lowers the costs, but it also reduces the CO2 footprint of the supply chain, since a lot of trucks running between the argon plants, the air separation plants, and the customers are eliminated. It enables supply chains at the scheme of a gigawatt and above, where the simple amount of shipping argon into the wafer industry is not viable, and hence it enables supply schemes for very large ingot and wafer plants. Selective emitters are very much discussed and used by the industry today, and there are several processes available which which are using different chemicals and gases. Selective emitters are used because low contact resistance is needed around the fingers, around the contact fingers, and this is done by this needs heavily doping, while the other areas in between the fingers require light doping in order to improve the surface passivations. There are a number of processes available which have been developed by equipment manufacturers and have been adopted by the customers, by the industry. One possibility is to start with a cell which has a whole heavily doped surface. Then a protection layer is printed on the heavily doped areas, and the rest of the cell is etched back. This requires the use of big amounts of hydrofluoric acid and nitric acids. The other processes starts with lightly doped cell surfaces and add the heavily doped in a second step. Several processes available. One of it is laser doping, which uses phosphoric acid and then lasers to activate and incorporate the phosphorus into the cell. Another one is ion implementation, which needs phosphine gas, or oxide mask, which grows a very thin oxide mask on top of the cell, which is then lasered and using phosphorus oxychloride for the phosphorus doping. All of these forementioned processes require standard processes and chemicals, standard process gases and chemicals, which do not provide significant challenges to the materials industry. Some printing processes are under development, like doping paste, like printing doping paste or printing silicon ink, which are unique material solutions. Selective emitter are reported to enable cell efficiency gains of 0.2 to 0.5% absolute efficiencies. Another possibility to improve cell efficiencies is to use backside passivation, which is needed to suppress surface recombination and is required for especially for very thin and very high efficiency solar cells. The most discussed layer for backside passivation is aluminum oxide, which has proven to be highly effective as a rear side dielectric. And aluminum oxide layers can be deposited by using either chemical vapor deposition or atomic layer deposition processes. The precursor for these layers is trimethyl aluminium, which is then reacted with an oxygen source, which can be nitrous oxide or moisture. Trimethyl aluminium is a very common molecule in optoelectronics, semiconductor applications, but it is a new molecule for the solar industry. It is a pyrophoric liquid, which means it ignites spontaneously in contact with air. So a safe delivery of the molecule to the point of use is key to enable the adoption by the industry. Backside passivation has shown in pilot runs to be able to improve cell efficiencies by 0.5 to 1% absolute level. One potential step change to the industry is the change from P-type to N-type wafers, but this poses some challenges for supply chains for both wafers and materials. N-type wafers prevent the degradation of minority carrier lifetime, since there is no boron present in the N-type wafers, and boron-oxygen complexes are known to reduce the lifetime of minority carriers. So higher efficiencies is possible. Also, the minority carriers in N-type wafers are electron holes, and electron holes are less subject to recombination with transition metals, which means N-type wafers can tolerate higher level of transition metals. The industry can use lower purity, lower cost wafers, which helps to bring down costs. One of the challenges for this is the availability and costs of N-type wafers. Another challenge for this technology is the p-doping, because N-type wafers need a positive doped emitter. This doping is mostly done by boron tribromide, BBr3, which is an equivalent doping material to phosphorus oxychloride, which is used as N-type doping for p-type wafers. Boron tribromide is used today as a niche product in semiconductor applications. However, supply chains are not yet ready to support N-type wafers if they take off in the industry. So developing supply chains, developing synthesis, developing supply solutions for the industry is another challenge for material companies. Change from P-type to N-type wafers has the potential to improve absolute efficiencies by 1.5 to 2%. Another area which is very interesting is texturization. Solar cells need a rough surface structure in order to improve light scattering and also in order to reduce surface recombination. Some of the texturization is done by wet chemicals. Another area which is very interesting is use of reactive ion etch. Some processes have developed by OEMs and industry users, which are using sulfur hexafluoride, chlorine and oxygen gas mixtures, and these have shown to be able to improve cell efficiencies by 0.4 to 0.7% on an absolute level. The problem of this process is that SF6 is a very harmful greenhouse gas. One molecule of SF6 is 23,600 times more harmful to the global warming than CO2, so it doesn't fit very well into the solar industry. And one alternative that is becoming popular is fluorine gas, which is available today as a cost-efficient, environmentally friendly alternative. And the new thing about fluorine is not a very new molecule, but a new thing that is available is the the economically viable production of on-site fluorine. And the good thing about on-site fluorine is fluorine is a very hazardous and toxic gas. By making it on-site with electrolysis, it can be the whole supply chain can be at a very low pressure without the need of pressure regulators, which are the critical parts and have been proven as a source of safety issues. Making fluorine on-site does not need pressure regulators, and also making it on-site allows to have very low inventories of fluorine, which improves the safety. I'm going to talk a bit more about on-site fluorine on the next slide. It's also one of the other processes where it is used is to replace NF3 or SF6 for PECVD chamber clean. Linde have worked together with Oerlikon to develop this process on Oerlikon's thin film silicon solar tools. You can see on the chart the performance curves of NF3 versus fluorine. And the y-axis of the chart is the etch rate, which indicates the cleaning performance versus the flow. So fluorine has a higher performance than NF3, and higher performance here means that you can choose to either go for a very fast clean, which improves the throughput by 35 to 50%, or you can use the same flow to achieve 20 to 30% mass savings, which means cost reduction. Using fluorine allows you to enable have no undesired greenhouse gas emissions, since fluorine has a global warming potential of 0. It is a proven solution for thin film silicon solar cells. On-site fluorine has been used by Malibu and by Oerlikon Solar for more than a year. And there are further developments ongoing for heterojunction solar cells, or also silicon nitride anti-reflective coating, where also fluorine can be used for in situ CVD chamber cleaning. And I'm coming back to I'm coming back to conclude with one of the slides that I used earlier. Materials and material technology and material innovation are helping to reduce material costs, to reduce the costs and improve the efficiencies of solar cells. You can go to local production of nitrogen, hydrogen to reduce the cost. You can recycle argon to enable large-scale wafer plants and reduce costs. Fluorine can both help to reduce costs and increase throughput. And new materials like BBR3 or TMA can enable new processes which help to improve cell efficiencies. Thank you very much for your kind attention. I'm available for questions right now. We are also at the IPVEA booth in Hall 3, and we'll be more than happy to talk with you and discuss material innovations with you there.
Thank you, Mr. Weisheit.
Have we got time for questions? Or?
Right on time, perfect.
Okay, thank you very much.
We have a tough time schedule, therefore I ask now directly for Mr. Wohlfahrt from Singulus.